Hey everyone, and welcome to This Explainer. I am absolutely thrilled to be your guide through this topic today. So often, physics gets a pretty bad rap. A lot of people just picture this giant, intimidating wall of complex math and really abstract symbols. But honestly, that's not what physics actually is. At its very heart, it's simply a practical language. It's a way for us to read and understand the change that's constantly happening in the everyday world around us. And today, we're going to build your conceptual toolkit so you can do exactly that.
Okay, let's dive right in because this quote completely changes the game. When a train pulls out of a station and you feel your body lean backward, well, that's physics. When a hot cup of coffee left on your desk gradually cools down over the morning, that's physics too. When you're riding a bicycle down the street, you are quite literally a walking, pedaling physics experiment. Hopefully wearing a helmet, of course. Physics isn't locked away in some sterile laboratory. It's the operating system of your daily life.
So, to completely demystify all this, we've got a really clear roadmap for today. We're going to cover the language of change, forces in motion, the currency of energy, waves and electricity, and finally, powering our future.
All right, part one, the language of change, building the foundation. This brilliantly illustrates how we actually go about making our observations measurable. When you look at a velocity time graph in a physics textbook, you'll almost always see this formula for displacement during constant acceleration, and it includes this kind of random-looking fraction of 1/2. But I promise, it isn't magic. If you look at the shape on the graph, the area under that line represents your total displacement, and it's made up of a rectangle and a triangle. Well, the area of a triangle is 1/2 its base times its height, right? That 1/2 is purely geometry. It's just translating visual change into a nice, neat mathematical model. Now, nature definitely likes to throw us a curveball sometimes, like when an object is in free fall and the distance it drops increases with the square of time. But we can easily fix that using a neat process called linearization. By plotting the distance against the square of time, we take a tricky, curved relationship and transform it into a perfectly straight line. This simple visual trick makes physical relationships incredibly easy for us to test, compare, and verify.
Moving on to part two, forces in motion, why things move. Let's do some rapid-fire myth-busting with a few foundational terms, starting with distance versus displacement. If you run a full lap around a 400-meter track, your distance is 400 meters, but your displacement? It's zero. Literally zero, because you ended up exactly where you started. Displacement always cares about your direction, and here is a absolutely crucial pivot. A negative velocity or acceleration doesn't automatically mean slowing down or something bad. Actually, scratch that assumption entirely. A negative sign simply points in the opposite direction of whatever we decided was positive. That's the whole shebang.
Okay, next comparison, mass versus weight. People mix these up constantly. Mass is your resistance to acceleration, which we measure in kilograms. Weight, on the other hand, is a gravitational force pulling on that mass, measured in newtons. Think about it this way. If you take a rocket to the moon, your mass, the actual physical amount of you, stays exactly the same. But your weight, the gravitational pull on you, that drops drastically because the moon's gravity is so much weaker. And that brings us to a truly massive concept, inertia. Objects just don't naturally want to stop moving. If you slide a heavy book across a table and it eventually comes to a halt, it didn't stop because it somehow ran out of force. It stopped because an invisible force, friction, acted upon it. If you were to totally remove friction and air resistance, that exact same book would literally keep moving forever, straight out into deep space. So how do we decode all these interactions? We use a super structured logical procedure called a free body diagram. First, you just isolate the object. Draw it as a simple box or a dot. Then, map out where it physically touches other things. Those are your contact forces. Add gravity, which acts from a distance. The absolute golden rule here: only draw the forces acting on the object, not the forces the object applies to other things. Finally, set up your coordinates, and you're good to go. When we apply those exact steps, we get a perfect free body diagram. Imagine our isolated block. We've got the downward pull of gravity, totally balanced out by the upward normal force of the table. Then we have an applied force pulling it in one direction, while the friction force fights back in the opposite direction. By stripping away all the messy visual noise of the real world, we can perfectly predict exactly how this block is going to accelerate. Section 3, the currency of energy, the driver of change. In everyday life, carrying a really heavy bag of groceries horizontally down the street feels like a ton of work, right? But in physics, if you are moving horizontally while supporting the bag vertically, you are technically doing zero mechanical work on that bag. No way, right? Well, in physics, work specifically means a force acting along the exact same line as the displacement in order to transfer energy. Now, what's really interesting here is how beautifully this energy transforms. When an object is dropped, its total mechanical energy stays exactly the same the whole way down. But as it falls, the gravitational potential energy perfectly trades places with the kinetic energy. The energy doesn't just disappear, it simply changes its currency from height to speed. All right, time for another myth-busting moment, and this one might actually surprise you. Temperature and heat are not the same thing. Not at all. Temperature is just a measure of the microscopic, chaotic motion of particles. Heat, on the other hand, is the actual transfer of energy from a hotter object to a colder one. For example, a tiny little spark from a firework has an incredibly high temperature, but it contains very little actual heat energy compared to, say, a lukewarm bathtub.
Moving right along to Section 4, Waves and Electricity, Transferring Energy and Information.
So there are basically two main ways a disturbance can travel. In a transverse wave, like snapping a stretched out rope, the rope itself moves up and down while the wave travels forward. The motion is perpendicular. But in a longitudinal wave, like the sound of my voice reaching your ears right now, the air molecules are actually bumping back and forth in the exact same direction that the sound is traveling. The absolutely crucial point to remember is that it is the pattern that travels, not the material. When you look at a transverse wave, the amplitude is how tall it gets. That shows you the energy level. The wavelength is simply the distance before the pattern repeats itself. If this were a water wave out in the ocean, the water itself is just bobbing up and down in place. It's the disturbance that races across the sea, not the actual water. And that brings us to a really beautiful phenomenon called resonance. Every single object has a natural frequency it likes to vibrate at. If you push your child on a playground swing at exactly the right time, matching their natural frequency, they go higher and higher. That is resonance in action. It's the exact same physics that allows a guitar string or flute to create a gorgeous, sustained musical note. Electricity actually uses really similar principles of flow and energy transfer. We can see the elegant rules of electrical circuits right here. In a series circuit, there is only one path, so the current flowing through every single component is exactly the same. But in a parallel circuit, the path splits. Charge is always conserved, so the current divides up, but the voltage, which is the energy push across those branches, remains exactly the same. Finally, Section 5, Powering Our Future, Physics in Society. We are going to take this entire conceptual toolkit we just built and apply it to the real world. When we look at societal energy grids, whether we're talking about fossil fuels, nuclear power, wind, or solar, physics doesn't take sides. Instead, it gives us 5 completely impartial lenses to weigh the trade-offs. We look at reliability, can it deliver power when it's needed, environmental impact across its entire life cycle, safety and the consequences of failure, the economics of building and operating it, and fairness in how those resources are distributed globally. The reality is, no single energy source is perfect across all 5. Because our electrical grid doesn't have some massive built-in reservoir, supply and demand have to match perfectly, literally every single second of the day. As we move to more variable sources like wind and solar, grid storage really becomes the missing puzzle piece. Whether we pump immense volumes of water up a mountain just to release it later, build massive battery banks, or compress air deep into underground caverns, physics tells us exactly how efficiently we can store that energy to balance our future grid. We have moved from a simple ball rolling down a ramp all the way to the complex electricity powering our entire cities. Physics is simply the language we use to decode all of it. The world around you is always in motion, full of invisible forces transferring energy and propagating waves. Now that you've got the conceptual toolkit, how are you going to read it? Thank you so much for joining me for this explainer, and keep looking at the world with curiosity.